Okay, so the fact that I could still turn in last night, I haven't graded the exams yet. I think I already started working through the other section, and based off how quickly it's going, I'm hoping to get a lot of them graded today. But my guess is I won't have them all done. I think they should all be done by the time we start class Wednesday. So I'll be able to have a little bit more to say about them. Looking at kind of the average of the multiple choice, I think the average will probably be around where I want it. There's an off chance that if I have a low enough average across my sections, I may apply kind of a small curve to kind of get that average to be at least as high as a 75. Although, like I said, based on the multiple choice, I think it's going to be around there. So yeah, I'll be able to talk a little bit more about that Wednesday. I'm hoping to have all those graded by then. I'll also kind of housekeeping before I don't forget to mention stuff at the end. We'll have an online quiz today. Let's do before we start class Wednesday. And then I will assign a Learn Smart. And I'm not sure when I'll set the exact due date, but I think it's going to be next Monday. So it won't be for the stuff we're going to talk about kind of this week, but it'll be kind of the next chapter, or at least the end of kind of this chapter. So I don't think we'll get to that material until probably next Monday. So I'll probably have it set to be done and completed before we start class Monday. Right? But so Learn Smart should be pretty easy. 10 minutes, get on, just kind of get the points, get it done, and not graded for correctness, just a matter of getting that done. Okay. I think I said getting it done about 50 times there. So let's jump in to the slides for this week. So some of what we're going to be talking about is really stuff that we've already talked about, just in a slightly different context. So we did discrete random variables, and we've talked about just regular continuous variables. So now we're going to be looking at continuous random variables, right? So it's going to be like discrete random variables in the sense that we don't know what the outcome is going to be, but it becomes a little bit more difficult, right? So instead of being able to find the probability of certain outcomes here, all we're going to be able to do is find the probability over certain intervals. Right? And I'll explain this a little bit more in just a second. All right, this is a reminder, we can see a continuous random variable take on any value, right? You could go out to whatever decimal point, so 6.35179. So really we've got kind of a lot of different possible outcomes we can see this variable take on. Some of the variables we think about is income or interest rates. Right? I think what I have here is, so just like with discrete random variables, we're going to have a probability mass function or a probability density distribution. Right? So it's going to tell us the probabilities of seeing this random variable take on values across a certain range. So before it gave us the probability of seeing one specific value. Now this probability density distribution is going to be kind of like a probability mass function, but it's going to give us the probability over a certain range of values. Now the reason why we have to do that, we can use kind of a graph to do this. So I think what I make sure here, this probability density function, I'll write this as f of x when I go to the dot cam here in just a second. Okay. So that's not the dot cam. This should be the dot cam. Let it catch up here. So I have this probability density function. But I think about this random variable x, f of x, right, is going to be some function such that it's going to give me probabilities of seeing different values for x. So kind of my y-axis here is, think about it as the probabilities associated with these different x values. And the way that I was able to plot this line was every time I plugged in a value for x, I had that probability density function, f of x, that was spitting out at me these probabilities, right, or these y values that I could plot this entire line. Okay. So this is a little weird to think about. And it's a little, it kind of, I don't know, it's like infinity is always weird to think about. But I'll set this up with, let's think about a scenario where maybe we go back from continuous, go back to discrete. Let's say I had an example where I had 100 different possible outcomes, and every single outcome is equally as likely. What would the probability of any one outcome be? Yeah, so 0.01 or 1 out of 100. What if I had 4 possible outcomes? 1 over 4. What am I doing there? Really just 1 over the number of possible outcomes I have. The problem is, even if I think about let's say I can only see values in between 5 and 6. How many values are there in between 5 and 6? If it's truly continuous, infinite. So my number of possible outcomes for this distribution is infinite, which, in the limit, is essentially 0. So we end up with a truly continuous random variable. The probability of any one value, let's say the probability I see 7, that probability is actually 0. Right? And all I can do is find the probability that I'm in between, two values, like between 5 and 6. Now, I'll explain things in a certain way initially, where I'm saying think about if we were to be able to find this probability of one specific value, because I think I can kind of set up how we should be thinking about these continuous variables a little bit better, discussing it in that way. But we don't want to lose sight on the probability of any one value is actually 0 on this distribution. And that essentially that comes from the fact that there are an infinite number of values we could see, right? So the probability of any one value is 0. We'll use this a little bit today in some stuff that we do. Let's see, this doesn't go back, did it? Nope. Let the screen in class catch up here and we'll keep going. All right. So we can use this probability density function to find the probability over certain intervals, being in between two values. So some conditions that this function has to have, and we're really going to be talking about specifically just the uniform and the normal from here on out. We'll do the student t as well, but that's a ways out. So this function will have no jumps, right? So it's not like I drew this one like this. It's what you wouldn't see it kind of stop here and then jump up here and then keep going, right? And there's no jumps. The probability has to be 0 or larger, right? It's a probability. We can't see it go negative. And then here's one. We've actually already talked about this principle with discrete continuous random variables. So if I took every outcome for a discrete random variable, the probabilities of each one of those outcomes should add up to what? 1, yeah. Someone holding their finger up. So if we integrated this function from the very lowest to the very highest x value, essentially what that's doing for us is giving us the area under the curve. Well, I can think about it as every single, like if I had really infinitesimally small intervals, I could find the probabilities associated with them. So it's almost like I've got a million triangles underneath this distribution. And if I could find what that y value is, what that probability is for each one of those intervals, and then add them all up, well, essentially that's taking the probability of every possible outcome and adding them up. So the area under that curve is going to be 1. Because really, like I said, you could think about it as you're breaking this down just to the smallest rectangles, which would all have a probability associated with those intervals, add them all up, the probabilities of every possible interval there would have to add up to 1. And that's what integrating that function across that range would do. Okay. So I know they set things up a lot in calculus, thinking about there's a bunch of really small rectangles under a line. That's kind of what we're doing here. Now, I'm not going to make you do kind of like the integration. We've got ways that we can kind of deal with that and make it easier. But that is, kind of what we're doing, essentially. So, right, we've got this continuous random variable, all the possible values for x. The area under this curve is going to be 1. Okay? So the area that, under this curve from the lowest to the highest value, that area will be 1. It's just like we had more simple examples, but it's just like when we drew a Venn diagram and we had that rectangle which represented the entire experimental outcome space. We said that area would be 1. This represents the probability of every single possible x or every single possible outcome in that experimental outcome space. So the area under the curve is now 1. Right, so it's taking a different shape, but it's the same idea as what we're doing with the Venn diagrams. Okay. So what ends up being a little bit more useful than the probability density function is the cumulative density function. So the cumulative density function will tell us the probability that we see the value x, or what does cumulative mean? Anything below it, right? So when we were doing this with discrete random variables, it was like we didn't have an exact function, but we could, take the probability of 8 plus the probability of 7 plus 6 plus 5. We had a cumulative density function option in Excel with a binomial, right? Well, now we're essentially going to have a cumulative density function that has an exact functional form, right? So it isn't just a function in Excel, it's an actual function we could plot, right? So, you know, with this idea of cumulative, right, we've talked about this with like the cumulative relative frequencies and some other areas. Once we get to really high X values, what should the cumulative density function start returning close to? 1, right? If I put the maximum value in that cumulative density function, it would take, what's the probability I see the maximum value or anything below it? Well, that's every possible outcome. I have to see something, so that probability is 1, right? I will definitely see something in that range. As I get, you know, really, really small X values, that cumulative density function starts to get really, really close to 0, right? And what's the probability I see something that's just barely above the minimum or anything less than that? Well, that's a really, really small, right, closer to 0. So what if I wanted to find the probability that X is less than A? Or here I have less than or equal to A. Well, if I think about, I'd plot A here in my distribution. Once again, I could think about it as there's like really, really small rectangles, like a very, very infinitesimally small interval lengths that I could be adding up from A all the way down to, you know, wherever the distribution stops to the minimum. So the area under that curve from the very lowest value up to A, that would be what the cumulative density function would tell me, right? Add up all the probabilities of every possible value that's equal to A or anything below it, right? So I can think about this probability that X is less than or equal to A. I can simply write that as the cumulative density function, capital F, and plug A into that function. Okay. Does that make sense? Like I said, I didn't draw it out, but you can kind of imagine these really, really small rectangles underneath this curve if we were to add all of them up. That's what the cumulative density function is doing for us. What if I wanted to find the probability that X is greater than or equal to B? So there, what am I looking for? Well, now I want the probability X is equal to B plus the probability X is equal to everything above it, which would essentially be the area under the curve to the right of B. So there's a way that we can find this, right, kind of using that cumulative density function. So I'm going to draw this out for us here. So let's say I'm thinking about this scenario where I want the probability that X is what, greater than or equal to B, I think is what we had in the slides there. Well, if I use that cumulative density function and I plug B into it, what's that going to give me visually? Well, what that would actually give me is the probability I see B or anything below it, right? But I want the probability that I see B or anything above it, so what can I do? The area under the curve is 1. Yeah, so I could take that red area, subtract it from 1, and that would give me what I wanted, which was this blue area. Right? Or take the probability X is less than B, subtract it from 1 to get the probability X is greater than or equal to B. Where does that come from? Well, if I've got this, and I think about this as my event A, that's the same as 1 minus the complement, right? What's the complement? That X is less than B. Or 1 minus the cumulative density function where I plug B in, because that gives me the probability of seeing B or anything below it. Now, you might look at me and say, well, there's a problem with this, right? What could you argue is a problem that I missed at this point? What did I originally want? What was I doing here? Right? When I'd use that cumulative density function, that actually puts a quality on that value of B. But why doesn't that matter? Okay? So if I didn't have that, so just have X is less than B. Well, this is kind of tricky. That's the same thing as if I add in the probability X is equal to B, what did I do to this equation? What did I say this probability should be? Probability of any one value should be 0, right? The probability of any one specific value is 0. So I actually didn't change this equation at all. This is kind of like some almost like real analysis type math stuff. And then once I have this, well, what I really have is the probability that x is less than b. Actually, sorry, I wouldn't want to add this, and I could subtract that. Now what I have is the probability x is less than b and the probability is equal to b. I could combine those into being x is less than or equal to b. So it kind of makes the complement rule a little bit easier for us here because we don't have to worry about the equality. It doesn't matter which side the equality is on because the probability of any one specific value is just zero. Is 0. So we'll use that kind of moving forward. Right. So we could just subtract that cumulative density function from 1, and we get the probability that we're greater than or equal to b. What if I want the probability I'm in between two values? Well, there what I'm really saying is what's the probability I'm equal to a plus every one of these really small rectangles all the way up to b, right? So this kind of light gray shade area. How could I find that? Well, let's say I had this scenario where I wanted to find. I'm going to try to do this without a little bit different than I did last class. So I want the problem in between these two values. So the area under the curve in between these, right? So what I can do is if I use the cumulative density function, f of a, it would give me this area, right? Probably I see a or anything below it. Add up all those probabilities. What if I had the cumulative density function for b? Will that give me the probability of b or anything below it, right? So what I wanted originally was just what's the probability I'm in between these two. So if I take this kind of entire area of b and I subtract out the red area, now I'm just left with what's in between. Or I take that cumulative density function for the larger value, subtract the cumulative density function for the smaller value, and that would give me the probability I'm in between those two. Any questions on that? We're okay with that? See anything in the chat, so. All right, so kind of already covered that. What if I wanted the probability that I'm less than a or I'm greater than b, right? So I kind of want the tails here. Well, I could just think of that as if I could find that light gray shaded area, which was what we had just saw in the previous slide, was the probability in between a and b. I could just subtract that from 1, and I'd be left with this in the tails, right? So a lot of this is we're going to be doing this behind the scenes, especially once we get to the normal distribution. But this kind of gives us a basis for what we're going to do later on, where a lot of times we won't even think about what we're doing. And really what it comes down to is once I get used to using this cumulative density function, I'm really just trying to find certain areas under the curve, and like I know the different pieces have to add up to 1, right? I know that if I take this kind of brighter blue area and I add to that the light gray area, that's everything under the curve that adds up to 1. So if I can find one of these, I can automatically find the other. Okay. Any questions on this before we keep? Shouldn't be too bad yet. Oh yeah, we're good. Okay. So those are some kind of general, I don't know, topics, principles about the continuous random variables. We're now going to talk today about one specific type, and then kind of moving forward, we'll really focus on another type, which is the normal distribution. But today, we're going to focus on the uniform distribution. Okay? So the uniform distribution is going to be any variable where every value is equally as likely. Well, it's a little bit misleading because, right, the probability of any value is 0, so they all should be equal as likely. But what we'll change this instead to is every equal sized interval has exactly the same probability of occurring or is equally as likely. Okay? Excuse me, so the density function that we have for this is 1 over d minus c, where c is essentially our minimum value we could see, and d is the maximum value. So we're 1 over the range is really going to be our density function. And then 0 otherwise just means if I'm outside of the range, if I see something below or what's the probability I see something below the minimum or above the maximum? Essentially 0, right? Anything outside the range of the minimum maximum has a 0 probability of occurring. Okay. So I think the best way, and I'll come back to this slide, I think the best way to think about the uniform distribution is like this. So we've got this variable x. We can take on a bunch of different values. Right? So let's do, let's say it can range from 10 to 20. If I think about the very first interval of size 1, right? It goes from 10 to 1. That is going to be equally as likely. And if we remember, like what's up here on my y-axis, these are going to kind of think about these as probabilities. Right? So what's the probability I see something in between 10 and 11? I can almost draw a bar there. And then what's the probability I see something between 10 and 12? Well, it's equally as likely because it's an equally sized interval, right? It's still an interval of 1. So it's going to have the same probability of occurring. And then what about the next interval, right? It's the same size interval of 1 has the same. So essentially our uniform distribution, we're just going to end up with a straight line, right? It doesn't have any curve to it, right? Because seeing certain values, right? Seeing the value of 11 between 11 and 12 is the same as seeing values between 19 and 20. So if I think about it this way, if I were to divide up this range, 10 to 20, into 10 equally sized intervals, right? All of size 1, so essentially like integers, right? What would the probability of any one of those ranges be? Well, first of all, if they're all of interval of size 1, I'm going to have 10 of them. So if they're all equally as likely, each one would have a probability of occurring of 1/10. Yeah. Now, a more general form, that probability density function told us the height of this distribution will be 1 over d minus c, or in our scenario, 1 over 10 minus 20, or sorry, 20 minus 10, or 1/10, right? So that's why when we're finding intervals of size 1, each one has a probability of occurring of 1/10. Okay? Now, what if instead we had that same setup, but I asked you, okay, what's the probability that I see this value x, or a variable x, take on an outcome between 10 and 12? Well, I know the height of this distribution, or kind of where my y-axis point would be plotted, or my y-axis. What point I would be kind of plotting on the y-axis there is 1/10. So notice, this is just the area of a rectangle. So I always say this, I don't know, I'm far enough removed from doing a lot of geometry stuff. You know, it's base times height or length times width, whatever you want to call it, right? So what's the width of this rectangle? Yeah, 2. What you were doing there was just taking 12 minus 10. You would then multiply it by the height of this rectangle, which we got that from that probability density function. So 1 over 10 or 2/10. Right? What you were really doing there was you took where your interval stopped and started, right? B and A. You can think about this was B, this was A. You multiplied it by 1 over your maximum minus your minimum, or we were kind of notating that as D minus C. And another way of writing this is, just simplify mathematically, this general equation. So you could plug 12 and 10 in, plug 20 and 10 in, you get the same thing of 2/10. But I also like to, I like to explain it first. I think it's really easier if you just think about finding the area of a rectangle and draw this out. Once you have the height of that distribution, now it becomes really easy to find the probability of a ton of different size intervals, right? Let's say I want to know what's the probability that you go from 14.4 to 15.6. Well, that interval is 1.2 times 1/10, right? And so it becomes a little bit easier, I think, to think about it as the area of a rectangle. But this general form of the equation will hold as well if you want to plug everything in there. So that's how we arrive at this density function that gives us the probability of being between any two values, right? Because really hidden behind this formula was the idea that we were doing width times times, or length times width, or base times height, however you want to think about that. Okay. Any questions on that? Anything at that point? We're okay with this? Double check there's nothing in the chat. Okay. So, if we're thinking visually here, if I look at the area between my maximum and my minimum, this becomes kind of weird. So before we were saying the area under the curve is equal to 1. It takes the probability of every possible event essentially and adds them up. Well, here, my curve is a straight line, but it still represents my distribution. So the area under the curve, which is the area under my line, up to my maximum and down to my minimum, this entire rectangle should have an area of 1, right? It represents my entire experimental outcome space because it's got the probabilities of every possible outcome in that interval. Okay. The height came from that density function, and I explained this intuitively, in that if we were to break up an interval into if we were to break up all the possible ranges for that uniform distribution into intervals of size 1, it's a little bit easier to think about because now how many times does 1 go into 10 essentially, right? How many of these intervals of size 1 were in 10? But that was how I explained where that comes from. But what we'll always hold is that the height of this distribution is just 1 over the range, right? 1 over the maximum minus the minimum. Okay. So some summary statistics that we can calculate for the uniform distribution. And I think the first one's very intuitive, right? So to find the mean or the expected value, you simply find the average of the minimum and the maximum. So why does that work? Well, we think about here, I'll use a different color to kind of identify this. I was going from 10 to 20, right? Well, everything is equally as likely. So I said in a normal mean, once we learned what the weighted mean was, I went back and said if we calculate a normal mean, it's really because what you can actually write it as is you're really weighting everything by 1 over n, right? So if you're weighting everything by 1 over n, well, everything's treated equally as likely. Every number has equal influence over the mean. Well, that's going to be the case here as well. So all you really need to know are where the minimum and the maximum are. And if you find the middle point in between those two, that's going to be exactly where the mean's at, right? So everything's equally as likely. So my mean will exactly split my maximum and minimum. So really all I have to do to find the mean is add those two values up, divide by 2. Just find the mean of those two values, the maximum and the minimum. So here we'd be at what? 15. Okay. So that's pretty intuitive, I think, to finding the mean. Now you'll notice this is a symmetric distribution, right? 15 exactly splits this in half, so there's 50% of the data on the right and 50% on the left. Right? So it's kind of a nice property that we have a symmetric distribution here with the uniform. Right? I'll talk about a little bit more in a second why that helps us out. So the other one is the variance, which is not as intuitive. It's just the range of possible values you can see squared divided by 12. So if you had that probability, go back up here. You had that probability density function, right? And you multiplied that by every single possible outcome for x, and then you subtracted the mean and you squared it. Sorry, you took every possible outcome for x, subtracted this formula for the mean, squared it, multiplied that by the probability density function. What you can prove mathematically is, if you write all that out, it simplifies down to just the range d minus c squared divided by 12 every single time. So it doesn't matter what your range is, your variance will always follow this formula. Okay? Kind of like the binomial, right? The mean was pretty intuitive, the variance wasn't as intuitive, but we at least have a formula we know can always find the variance for a uniform distribution. And then the standard deviation, as always, just the square root of the variance, right? That shouldn't be hard at all right now. Up to this point, I should say. Okay? Questions on that? This part shouldn't be bad. So let's try to actually kind of work some problems out here, and I'll address some other issues. So I pulled on an old cheesy movie from my childhood, which is Mr. Nanny. So let's say, the success of the first movie, they decide to do a second one. and this movie theater is trying to make popcorn, and I know that on average demand is anywhere in between 1 and 10 pounds, right? So they look at all the historical data. Demand is always somewhere between 1 and 10 pounds, but everything's equally as likely. So we've got a uniformly distributed variable. Okay? So what would be the mean pounds of popcorn demanded here? Well, if I've got this uniform distribution, right, and when we write this out, when it's written, oops, I forgot the U here. When it's written as uniformly distributed, here's your minimum, here's your maximum, or here's your C, here's that D value, right? So I'm going to identify 1 as my minimum and 10 as my maximum for all these possible values I could see X take on, or that I could see popcorn demand take on. I know they're all equally as likely, so I've got this uniform distribution. Okay? So the very first thing I would do in these uniform distribution ones is use that probability density function to find the height of this uniform distribution. Okay? So here for us, that would just be 1 over, remember D and C are just the maximum and the minimum. So 1 over the range, or 1 over 10 minus 1, is 1/9. So we can think about the height of this distribution is 1/9. Okay? If I'm looking for the mean, and that just sets me up for some future stuff as well. So if I'm looking for the mean, it's going to be the value that exactly splits this distribution in half, which would just be the middle point between your maximum and your minimum. So, well, this would be 10 plus 1 divided by 2, or 5.5, or maximum plus the minimum divided by 2. Right? I'm just finding the average of the maximum and the minimum there, or the mean of the maximum and the minimum. Now, I said before, what ends up being true is the mean is equal to the median for the uniform. It's a symmetric distribution. So what's the probability that I see an outcome below the mean, and what's the probability I see an outcome above the mean? Yeah, each of them are equally as likely. I know the area of this rectangle is 1, and so, right, the probability I see something above or below that mean, since it's also equal to median, should be 0.5. And that'll help me out in some kind of future problems, and we'll see why. Okay, so, but remembering, for these symmetric distributions, the probability you see something above the mean and the probability you see something below the mean are both 0.5, right? It exactly splits it in half. So we've got that mean there, okay? So the next question is, oops, we'll kind of get a refresher, but remember, right, if we want to find the area between two values, it's just going to be the area of a rectangle, so we can look at the width times the height, or use this general kind of equation, which is kind of really was expressing that, but doesn't connect with the visual as easy. Okay. So we've got this scenario where what's the probability that if this movie theater makes popcorn, so it's the same setup, that 9.5 popcorn, that if they make 9.5 pounds of popcorn, what's the probability they didn't make enough? So what's the probability that actual demand is something above 9.5, right? Or somewhere between 9.5 and 10, which would mean that they didn't make enough, right, to meet demand. Okay. So what we're really looking for there is, what's the probability that the actual demand takes on a value of 9.5 or greater? All right, so add up the probabilities of every possible value in between 9.5 and 10. That's one way we can think about it. So right away, I know this probability has to be less than what value? Yeah, right. If I know the probability that I see 5.5 or more is 0.5, well, then the probability I see 9.5 or more is only going to be something smaller than that, right? So I know it has to be something less than 0.5, and the visual here really reminds me of that, right? I know that if this is the entire distribution, it's exactly split in half by the mean. I'm looking for something that's going to be much smaller. But I want to go ahead and plug this in, right? Well, first I could just do it thinking of it as the area of a rectangle. So what's the base of this rectangle? Or what's the kind of width there? Well, it goes from 9.5 to 10. So 10 minus 9.5. And then what's the height of this distribution? What's the height of the rectangle? I had that earlier, was just 1/9. Enter that into our calculator, I think we get 0.056. Okay. Now you could have plugged everything into the general form of the equation, right? So we got B minus A over D minus C. So remember, B and A were just, where does my interval start and stop? So 10 minus 9.5. Then D and C is where does my uniform distribution start and stop? 10 minus 1. Sure enough, if we do this, we get that same 0.056. So either way works. Like I said, I just think drawing it out and thinking about it as the area of a rectangle just is a lot more intuitive and a lot easier for most people. Okay? But either way will be a kind of work there. Okay? I'm moving a little bit too quick here. So any questions on this? So if we go back, that's that 0.056. Okay? And here's some great other footage from the movie. You should watch all old Hulk Hogan's old movies. I mean, some of them are so bad they're hilarious. So this is probably one of the ones that's like that. But so here's the work. I kind of redid this for us, right? We plug everything in. What about if I ask, what's the probability we see exactly 9.5 pounds of popcorn demanded? Well, right away, what should this probability be? Yeah, I said earlier the probability of any one value should be 0, right? But let's try to kind of think about why that would be the case with this uniform. So we had what, 1, 10, and I wanted the probability of exactly 9.5. So if I think about my cumulative density function here, not cumulative, sorry, just my density function, because it's not cumulative, it's looking for the probability between two values. Where would my interval start and stop if I wanted exactly 9.5 pounds of popcorn demanded? Well, I know that the uniform distribution starts and stops at 10 and 1. But my interval actually starts and stops at the same point. So I really end up with 0 over 9. And it doesn't matter what example we're looking at. If I'm looking at the probability of one value, this numerator will always be 0. So 0 over anything is always 0. So this even proves to me, this uniform distribution density function will prove to me and remind me, or even if I work it out, the probability of exactly one value will always be 0. I'm going to have that in the slides, but I want to do some additional stuff that's not up there. So if we go back to the last one, okay, so we know the probability of any one value is 0, right? What if I wanted the probability I see, I'll use a different color here, demand be between 2 and 2.5? For my previous work, why should I be able to come up with what that probability is pretty quickly? Yeah, so what you're saying is this interval had a width of 0.5 or length of 0.5. This interval is a width of the exact same, 0.5. So equally sized intervals will have the same probability of occurring. If I want to go ahead and plug the values in, I can, right? 2.5, I'll plug in 2.5 and 2. My maximum and minimum of the uniform distribution haven't changed. Well, that numerator, if I take 2.5 minus 2, still ends up being 0.5, right? So it's going to look no different when I plug these numbers in, if it's 10 to 9.5 or 2.5 to 2 or 4 to 3.5, right? Any interval of size 0.5, I'll get the exact same probability that I see the outcome be in that interval. What if instead I wanted to do 2 to 3? Well, now if I know an interval of 0.5 has a probability of 0.056, an interval of length 1 should have a probability of what? Yeah, just multiply 0.056 by 2, right? Because, I could really, if I'm thinking about an interval of 1, I could break that up into 2 intervals of half, right? And we know that the probability of any interval of size half was this 0.056. So just multiply it by 2. Any other questions on that? What if I asked you for the probability that I see 9.5 or anything like below that. Like let's say the one where they made 9.5 pounds of popcorn. What's the probability that they made enough, right? Yeah. Yeah, right. The area under this curve or in this rectangle is 1. So if I had that area already calculated of 0.056, I know the area to the left of 9.5 has to just be 1 minus that, right? So, we start to kind of piece, look for different pieces here. Once we find one, it becomes a lot easier to find all of the others, right? Now, if I'd asked you that, what's the probability, and you didn't had any previous work done, what do you know the probability that demand was 9.5 or lower? What did it have to be greater than? Not just 0, but it has to be. Can't be greater than 1, right? Because the area of this entire rectangle is 1. So now I just want the area of this blue rectangle, right? Between 9.5 and 1. I know it has to be greater than what value? I think someone was saying 0.5, right? Why? Well, I know that the area to the left of the mean is 0.5. I'm now looking at a value that is greater than the mean. So the area to the left of that, or seeing something less than that, has to be greater. Has to be greater than that 0.5. Okay? And kind of the visual kind of helps us out a little bit. I know I've got a couple moving parts here. Try to use some different color, but we really could start manipulating this quite a bit, right? Looking for different areas, essentially under this curve. Okay? Any questions on that? Okay. So we already talked about this one where the probability is 0. I don't want to get you guys too far ahead of the other class. I can save this for next class. So I think we'll end there actually, unless we have any questions kind of about any of the stuff we talked about. Okay, like I said, I'll get that Learn Smart and that online quiz. We'll talk a little bit more about the exam when we meet on Wednesday. And other than that, just kind of nothing much to say. So I'll see you guys on Wednesday.